So before on this channel we've discussed the dot product, and it's when you take two vectors and you go in a certain way that it gives you a scalar quantity. But today, what if you want a vector quantity instead? Then we're talking about something else. We're talking about the cross product. So first of all, what is the cross product? Obviously, I've already said that the cross product gives you a vector quantity. It's also called the vector product, just like how the dot product is also called the scalar product. Now, what is the cross product? If you found a cross product of two vectors, what is it actually? So let's say we have two vectors, right here, two vectors, and these vectors will originate from a certain point. In this case, it's going to be like where my finger's holding it right there. So these two vectors can point in any way, any direction at all. But whichever direction the vector points, you will always be able to take a plane, or in this case, I'm going to use a piece of paper, and simply, the two vectors, there'll always be a plane the two vectors can be on. And you can take a pencil and try it. You'll realize that whichever way you hold the two vectors, there will always be a certain sheet that you can slide so that the two vectors are both flat on that sheet. And the cross product is simply just another vector that's sticking out perpendicular to that plane, or simply make right angles to both of the vectors. And that is just simply what the cross product of two vectors is. But then this is where we encounter the first problem. There is two ways that the yellow vector, or the cross product, the product, could go. I mean, it could be this way, it would make right angles with both of them, or it could be underneath. And this is where we have something called the right-hand rule. So what you do is you take your first vector, so I'm going to say the blue one is the first vector, and it's going to point directly towards the viewer. And I'm going to use the second vector, this one, and it's going to point, let me put it on the other side, it's going to point to my left. So it's going to be in that direction. So what you do is, first you stick out a finger into the first vector's direction. As I said, it's going to be towards the screen. Then you can point your middle finger into the direction of the second vector. So in this case, it's going to be that way. So you point it that way, and you stick your thumb up, and that's going to be the direction of the resultant vector. So in this case, the yellow vector will point up. But if it's reversed, then I'm going to have to try this. It's going to go like that instead. So the resultant vector, the cross product between the two, will give a vector resulting downwards. And another variation you can actually do this as, and I've seen at least my physics teacher use this, is that you can just simply point it out like this, the first vector like this, and you can just simply curl your finger towards the direction of the second vector, and your thumb will still point up to the direction of the resultant vector. It's just the right-hand rule. It's just how people like to use it. Personally, I use this. I see people using this to write in notation form to actually calculate the cross product. The cross product of two vectors, vector A and vector B, or you would simply write A cross B, is going to be the magnitude of vector A times the magnitude of vector B times sine of the angle between the two vectors, sine of the angle between two vectors, times n, where n is going to be the unit vector in the direction of the result of the cross product. Now you're probably already asking, how do you even get this? The truth is, I've read the proof and it's quite long and it's going to make the video quite lengthy, so I'm just going to skip the proof for now. But if you're really curious into it, then stay around for a bit, and I'll probably post the proof up. I'll probably upload the proof up once I get the video going, once I understand the proof myself. But what about more mathematically, rather than just sticking your fingers out and working out n? How can you actually find the cross product of two vectors? It requires a bit of maths and it's a bit confusing, but we're still going to do it because it's obviously a lot easier than the actual proof. So I'm going to pass it on to my other guy now. All right. So when we actually have the cross product between the two vectors, what we're actually finding when we're doing it mathematically is that the cross product of these two vectors is simply going to be the determinant of the following matrix. This is the determinant sign. It's going to be determinant of, first row will just contain simply the unit vectors in each directions, while in each column will contain the components, the AX, AY, and AZ, which is the X, Y, Z components of the first vector A, and the second one will just simply have BX, BY, and BZ. I've seen people complaining about my notations in the first video, so in my dot product video, so I'm going to correct it here. So how do you actually find determinants? So this is a method which I found personally quite easy. So what you do at first is you're going to rewrite these two rows out here. It's just for working out, so I'm going to rewrite it in red so you can just see it. Unit vectors, and then AX, AY, BX, BY. So this is just for notation. This is just to make life a lot easier. So then you draw diagonal lines like this, this line, and this line. Now you can multiply everything on that line, and you're going to add them. You can add these three. I'm going to write add. Then you're going to do the same up in the other direction. So these, and these. But instead here, you're going to subtract them instead. So I'm going to add, I'm going to multiply these first row. So it's going to be AY and BZ. So it's going to equal AY, BZ. And it's got an I and there, plus
AZ and BX, AZ, BX times J, plus X row, AX, BY,
with a K on it. Now we're going to start subtracting. We're going to go up the other lines now. Minus, we got an AY, BX with a K.
Minus again, because it's still got minus, AZ, BY, I. Minus again, I'm going to do that here because it's going to run off. AX, BZ.
Of J. Now you've got this. Now these can be grouped together more, so it's a bit more compact. So you can look, these two have got common terms, they both got I's. So you can actually rewrite that as AY, BZ minus AZ, BY, I. Plus, the next one, we're going to look at the J's. We got an AZBX minus AXBZ J plus the K's AXBY minus AYBX K. You might have seen the trend. You might have seen what happened while we were doing the vectors. You might have seen the pattern in it. But this here, this is basically the cross products between the two vectors, between vectors A and B. So I'm going to summarize it down here. So therefore, simply move this a bit lower so we actually have a bit more space. Simply vector A times vector B, cross vector B, will equal, I'm going to write it in this form, it's going to be AY, BZ, so the Y component of A times the Z component of B minus the Z component of A times the Y component of B, that's going to be the X component of the cross product, times AZBX, Z component of A, X component of B, minus the X component of A, Z component of B, that's going to be the Y components of the resultant vector, and going to be AX BY minus AY BX. And that right there, this is the cross product basically. If you're not bothered with right-hand rules or you're given numerical stuff and you prefer to work it out that way. So then you're wondering why we actually even have to bother with the cross product. One major use in cross product is in a field in something called torque. Torque is just simply tendency of a force to rotate around its axis. So like this thing has got torque in it. So how do we work out torque? Torque is the cross product between what we call the displacement vector and the force vector. Displacement vector is the vector from the rotation point out to where the force is being applied, so it's right there, against the force, the vector of the force. So I'm going to apply a force this way, that's the vector. The displacement vector is that way, so you can work out the torque when I push it here to be using the first vector times the second vector, because I'm going to push like this, second vector, so that means the torque will be pointing directly upwards. So when I do this, like this, the torque will be pointing upwards. And yeah, thank you very much for watching my video on the cross product. If you really want to see the proof, I will put the link in the description once the video of the proof is online. I'm not sure when yet, but it's going to be sometime. And yeah, thank you very much again for watching my video. If you like what you see, then you can click like and subscribe and whatever. And I'll see you again soon. Goodbye.